A summary of analyzing the graphs of f prime of x and f double prime of x. Alright, let's review the information that we can find given the graph of f prime of x. We can find a lot. If f prime of c is 0 or undefined, then c is a critical value of f. If we see that f prime is positive, then f is increasing, and if f prime is negative, f is decreasing. So we can apply the first derivative test. If f prime changes from positive to negative at c, then f of c is a local max. And if f prime changes from negative to positive, then f of c is a local minimum. More than that, we can find concavity from the graph of f prime. We can determine that f is concave up if f prime is increasing, and if f prime is decreasing, then f is concave down. So what that means is that if f prime changes from either increasing to decreasing, or f prime changes from decreasing to increasing, then cf of c would be an inflection point of f. So if there's ever a change in f prime from increasing to decreasing or vice versa, then there's a change in concavity, and change in concavity means inflection point. And now we have an example. We're going to let the following be the graph of f prime of x. We're going to find each of the following and justify. So whenever I'm given a graph, I want to label it with what graph that represents. So this graph here is f prime of x. So that's very important. We're not reading this for sort of face value. Like, this isn't the graph of f. We're answering questions about f given the graph of its derivative, f prime of x. So in part A, we want the x values of the critical values of f. So critical values, one of the best things that you can do is think about its definition, and that's going to be your justification. So it's almost like we're going to start with the justification first. The critical values happen wherever f prime is equal to 0 or is undefined. Well, f prime, here's my graph of f prime. Where does f prime equal 0? Well, those are my x-intercepts. So those two x values are -2 and 1. So we have x equals -2 and 1. And I'm going to put BC because f prime equals 0. So notice we put our justification first. So the critical values happen at x equals -2 and 1 because f prime equals 0 there. So now what are the intervals of increasing or decreasing of f? So let's go ahead and again think about increasing first, and its justification would be, well, f prime would need to be positive. So f prime would need to be greater than 0. Let's start with increasing. Well, that means that f prime needs to be above the x-axis. So this f prime is above the x-axis from 1 to infinity. So we're going to go ahead and write that f is increasing from 1 to infinity because f prime is greater than 0. And then we'll go ahead and finish out the problem by figuring out where f is decreasing, and that's going to be wherever f prime is less than 0, strictly negative, below the x-axis. So this graph of f prime of x is below the x-axis, well, from -infinity to -2, but right at -2, f prime of x is equal to 0, not less than 0. So I don't want to just include one big giant interval. I want to break it up at -2 and continue from -2. So, and from -2 to 1. And again, because f prime is less than 0 there, because f prime is negative. Now, where are the x values of any local minimums of f? So we know that we have a local minimum of f if f prime changes from negative to positive. So as I look at this graph from left to right, well, the first thing is that local mins and maxes can only happen at critical values. So we already found our critical values to be -2 and 1. Well, at -2, as I look from left to right, f prime is negative and then it stays negative. So that means that at -2, there's actually not a local min or a local max. At 1, f prime of x goes from negative to positive as I look from left to right. So I'm below the x-axis to above the x-axis. That means on my original graph of f, my function's going from decreasing to increasing. So I do have a local minimum at x equals 1. So I would say x equals 1 because f prime changes from negative to positive. And we basically already answered part D. There are no local maximums because our only two critical values were negative 2 and 1, and negative 2 had nothing going on there. So there are none for part D. And now for part E, let's move on to concavity. Find the intervals of concavity of f. So here we have to remember we're looking at the graph of f prime of x. So what we're looking for to find intervals of, let's start with concave up. To find intervals of concave up, we're looking for wherever f prime is increasing. So as I look at this graph, where is this graph of f prime increasing? So I can see that it happens from negative infinity to negative 2, and this graph is also increasing from 0, right? So we don't want to say negative 4. That's a very common mistake. We're not reading our intervals off of the y values. We're reading them off the x values. So we say that f is concave up. So I'll go ahead and put f. F is concave up from negative infinity to negative 2 and from 0 to infinity. Sorry, I ran out of space there. Because f prime is increasing. So let me go ahead and make a little bit more space right there. Because f prime is increasing. And so that means that f is concave down on, we can see this part that's left over here, from negative 2 to 0. And that's because f prime is decreasing. So wherever f prime is decreasing, that is where f is concave down. And so that means we can find the x values of inflection points. Well, we know that the graph of f switches from concave up to concave down because f prime changes from increasing to decreasing at negative 2. So it turns out that x equals negative 2 and x equals 0, because at 0, f prime changes from decreasing to increasing. So x equals negative 2 and x equals 0 are inflection points because f prime changes from increasing to decreasing or decreasing to increasing. So either one, because that would indicate a change in concavity of f. Given the graph of f double prime of x, what can we find? So if f double prime of x is positive, then f is concave up, and if f double prime is negative, then f is concave down. So the graph of the second derivative can really only tell us about concavity. So if the second derivative at some number c is 0, and the second derivative changes sign at c, then cf of c is an inflection point. So what we're looking for is places where f double prime crosses the x-axis. So f double prime can't just equal 0. We need the second derivative to change sign. We need to actually cut or slice through that x-axis, and then we would have an inflection point. We can also determine if we know critical values. So if we were to know that c is a critical value of f of x as just a piece of information that's been given, well, if we look at the graph of the second derivative at c and we find that that's a positive value, then we know from the second derivative test that f of c would be a local minimum. And if we had, again, that critical value and we looked at the graph of the second derivative at that critical value and got out a negative number, well, then f of c is a local max because then we'd have a concave down function. So again, we're more limited by what we can find from the graph of the second derivative. In this example, we're going to let the following be the graph of f double prime of x, and we're going to find each of the following and justify. So again, we're going to label this as f double prime of x. We always want to label our graphs. So we're going to find the intervals of concavity of f. So f would be concave up, wherever the second derivative is positive. So wherever this graph is above the x-axis. So we can see that this graph is above the x-axis from negative infinity to 3 and from 5 to infinity. So we have negative infinity to 3 and 5 to infinity, because, I'm going to sneak a because in here, the second derivative is positive there. So that means that f is concave down wherever f double prime is below the x-axis. F double prime is negative. So that's from 3 to 5 because the second derivative is negative there. So for part B, we want to find the x values of inflection points of f. So what we're looking for is wherever the second derivative changes sign. So not just equals 0. We need the second derivative to change sign. So the second derivative is positive, and then it switches to negative at 3, and then at 5 it was negative and switches to positive. So we couldn't have just a bounce off of the x-axis. That would not be an inflection point. We actually need it to cross the x-axis, either from positive to negative or negative to positive. So we have x equals 3 and x equals 5. Because f double prime, we can put changes sign at these values. So what that means is that f changes concavity. So that's what it means as a result. Oops, concavity. And finally, in part C, we have suppose x equals 2 is a critical value of f. So we're just being given that piece of information in this problem. Determine if f has a local min or a local max at x equals 2. So what we are interested in is the sign of the second derivative at 2. So here's 2. If I go up to the function, I can see that that value is positive. It doesn't even really matter what the value is. So since f double prime of 2 is greater than 0 and x equals 2 is a critical value, we know by the second derivative test, doing some abbreviating here, that there is a local minimum at x equals 2. So since the second derivative is positive, remember that would imply that the original function is concave up. So if I have a concave up function at something that we know is a critical value, then there has to be a local minimum at that particular value.